Hi everyone, today we're going to talk about the Taylor series. So the Taylor series can be used to calculate the value of an entire function at every point and of all of its derivatives if the value of the function is known at a single point. So first, let's talk about the basic formula for Taylor series. So the basic formula is and the expression of the Taylor series is that fx equals to fa plus f derivative a and the second derivative plus the third derivative and so on, and until to which is the basic formula. We can see that as the derivative continues, the number here increases and the power gets up to, and finally it is in. Here we can take an example of the graph of cosine x. We can see that this line here is the original line of the cosine x. And for the term of degree of 4, it becomes like this. And for 8, seems like this. And here is 2. So this is graphs of cosine x and sum of the partial sums of its Taylor series. So it is very clear from the graph. And now we can take a real example here. The title is given f of 3 equals to 6. A derivative f of 3 is 8, and second derivative f of 3 is 11, and all other higher order derivatives of fx are 0 at x equals to 3. And assuming the function and all its derivatives exist and are continuous between x equals 3 and x equals to 7, the value of f of 7 is a 38.0, b 79.5, c 126.0, d 331.5. Now we can look step by step. So first we can see the Taylor series. Here it should be fx plus h equals to fx plus the first derivative fx h plus the second derivative h squared plus the third derivative this is the same as above, as here I wrote x plus h and the expression is a, so it is the same. And we can get information from the title that x equals to 3, h equals to 7 minus 3, which is 4. and then we just apply these numbers in it. So it is f of 3 plus 4. Like this. And so on. And then calculate it. It is f of 7 equals to, so we can know from the title that f of 3 is 6, and plus 8 multiply 4, and 11, here's 16. And since all other higher order derivatives of f of x are 0 at x equals to 3, so we don't need to calculate them. Those are all 0. And then we just add them together, which is 126. So it is very easy.
So today I'll be introducing the Maclaurin series. So Maclaurin series is very similar to Taylor polynomial. It's just a special case of Taylor polynomial that uses 0 as our single point. So instead of fx, we are going to have f0 now, and the first term becomes f0 plus f derivative of 0 times x over 1 factorial plus f second derivative of 0 times x squared over 2 factorial plus f third derivative of 0 times x squared x cubed and over 3 factorial, and so on. So that there is the a on the top of the factorial is eliminated, so that only x and its factor is remain. So the whole formula will become from n equals 0 to infinite not 0 times xn over n factorial. So Maclaurin series is a power series that allows one to calculate an approximation of a function fx, f prime x and f prime x for input value close to 0, given that one knows the value of successive derivative of the function is 0. So like in many practical applications, it was equivalent to the function it represents. So basically, the real application of Maclaurin series is that when the computer was computing a lot of function with like complicated numbers, it cannot actually be just directly calculated. Like for example, if you're trying to use the basic plus, minus, times, and divide to calculate it the e to the power of 1.05, you're not actually going to just like compute it without using a calculator, or like the calculator itself cannot know like what is the real number of it. So it will perform a Maclaurin polynomial to get a estimation of the approximation of the value. So in many practical applications, it is equivalent to the function it represents, so that the calculator is able to get out a value. the Maclaurin series has a remainder that you need to know, so that it was the possible error that you can get. So Rn stands for remainder, and whatever you get for the Maclaurin series, for example, the third degree, you need to go beyond to the next degree, in order to find out the possible error for the whole function, so that it was applicable, and it was, like there's a certain range of error between it. So there's two questions about Maclaurin series. One is directly for the Maclaurin series, and the second is for the remainders. So before looking at these questions, there are several formula for the Maclaurin series that we need to recite. So for the first one is Ex. So the Maclaurin of Ex would be just n equals to 0, infinite, x, n. So this is the value that I'm talking about, so this is the formula that we need to compute for this value. And the second will be sin x, what equals to n infinite, and it's negative 1 n, and x 2n plus 1 over 2n plus 1. And this is obviously a alternating series because there's a negative 1. So the third one will be cosine x equals to n infinite negative 1 x2 n 2n. So you can see like it was the cosine and the sine cosine graph and sine are just like 1 degree different. That is because the graph of the cosine and the sine, one would be like starting here and have a curve here. Just start here, have curve here like that. And the second one will start here and have curve like that. So these two curves are very similar to each other's. And because like the derivative of sine is cosine, and the cosine's derivative is negative sine, so it was an alternating series. And basically 1 over 1 minus x would be n to 0 infinite xn, which is the simplest Maclaurin series that we need to recite. Then go back to these questions. So for these questions, it was kind of obvious. It should be cosine, since there's no +1 on here nor +1 on here, which means it could not be a sine. So C and D is crossed out. And from the basic formula, we know that the x would be n. So from the basic formula, cosine x, it would be n 0 infinite negative 1 n, and x2n over 2n without a 4n on the other side. But like if we replace the x with 2x, cosine 2x, so it becomes 2x over here, 2n and 2n factorial, and it becomes, so we split this part out, it should be 2n and x2n. So 2n, we know that we need this part is 4, so then n we stay here, it should be 4m x2n over 2n factorial. This is wrong here. So it was very obvious, and also you can see that there just shouldn't be any constant over here if it was only x, so it must be 2x over here, which is b. The second question is about the remainder of the polynomial. So the order of the Maclaurin series at least required to get an absolute true error at most 10 to the negative 6 in the calculation of sine 0.1. So let's just recall, like the remainder series is Rn x equals to xn plus 1 over n plus 1 factorial fn plus 1 c. So we're going to use 0.1 in this case for x. So Rn becomes 0.1, so, and it becomes 0.1 n plus 1 n plus 1 factorial. And because so that the derivative of the fx should be neither sine or cosine, because it was just the derivative of sine and cosine, as I mentioned before, and they both less than 1, so that this part should be less than or equal to 1, and we can just directly just replace this part with 1, not factorial, 1. So it becomes Rn 0.1 smaller or less than or equal to 0.1 n plus 1 n plus 1 factorial and 1 here, which should be eliminated. So if Rn 0.1 is smaller or less or is less than or equals or is less than 10 to the negative 6, and then this whole part should be less than, because it's Rn. It is possible to equal to Rn. So this one is 0.1 n plus 1 over 0.1 factorial is more than 10 to the negative 6, and by using calculator we were able to know that n is greater than or equal to 4. So we use the formula before. We can see that sin x can only contain odd terms, like it has 2n plus 1, so there's only odd term in it. So the only the smallest odd term greater than 4 should be 5. So this question should be 5. That's all. Thanks.